Hello everyone, in the series of basics of software defined radios and practical applications, we were discussing the software defined radio architectures, and this is part 3 of the same series. So we have discussed homodyne architecture, we have discussed super heterodyne architecture, and we know that heterodyne structures have the selectivity advantages over the homodyne structure. But we had seen that there is a problem of image signal which appears at the IF frequency if it is a particular distance from the LO. So we had seen that in the heterodyne condition we can actually select our LO and we can tune out this image signal, but in the real practical scenario basically this LO value and the IF values, they are fixed values, they are pre-selected values, we are not supposed to change them. So what could be one of the solution? One of the solution can be making the IF so large that the band pass filter will not select any component of this image frequency, and in this case the unwanted signal at the image location will be blocked by the RF signal. So it looks like a very easy and simple solution. So what is the catch here? What is the problem? The problem is that when we have the larger IF frequency, then our A to D converter and D to A converter, they have to deal with this frequency, and then by the Nyquist criteria we have to have the sampling rate which is more than twice of its IF frequency, which is the maximum frequency it will be achieving there. Now we do not want to put that constraint on the DAC and ADC, and that is why we have gone to heterodyne architecture in the first place. So it is one of the reason. The another reason is that if we have clock jitter in our clock which is sampling for the ADC and DACs, then there is a certain SNR degradation. So we can see this degradation, it is minus negative of 20 log 10 2 pi f in T jitter. This T jitter is actually the fluctuation of the sampling clock in the time domain. So basically what happens that because there are some phase noise there, it is not starting at a particular stance, it can jump little bit here and there. So it is called the incoming signals RMS jitter, which is coming from which is colliding with that LO. And the second factor in this expression is Fin, which is incoming frequency. So for sure when we have high IF, ADC or DAC has to deal with this this Fin, and then signal to noise ratio goes up. So it is degradation in signal to noise ratio. So what can be the solution for this one? One solution can be to avoid the high IF by providing the same IF in 2 conversion steps. So if it is frequency domain, and let us say this is our amplitude of the signal, turn response, then if suppose this is the RF signal we have to reach, it can be sum of IF1, then IF2 and then LO, right. So RF, FRF is a sum of FIF1 plus FIF2 plus FLO. It is equivalent to FIF plus FLO, where is FIF is actually summation of IF1 plus IF2. In that case, because our ADC is dealing with only the last stage, conversion stage, before it is applied to actually ADC, then this is the frequency which will be actually reaching at the ADC, and the sampling constraint will be decided by this frequency which is small. So sampling rate required will be small. Similarly the SNR which is defined by Fin, which is also decided by this FIF1. So the one solution can be down conversion process into 2 IF conversion steps. Now we know that we can increase the number of steps, but then in the heterodyne structure complexity increases. So we can avoid images due to IQ imbalance, DC offset, we can also avoid LO leakage, but it is at the cost of making the structure bulky. In dual down convergent structure it becomes even more bulkier, because we have two steps, two kind of alloys, two kind of filters, mixers, everything will be twice. So then what can be solution? That we want to retain the properties of the heterodyne structure, but we also want to have a compact design. So the solution comes in the form of digital IF based architecture. So this is a solution where we have the compactness of the homodyne structure, but selectivity feature of the heterodyne architecture. So this is the block diagram of the transmitter and receiver, which is the digital IF based architecture. So you can see that from the baseband we are directly having our I and Q data in phase quadrature phase data, and then a digital numerically controlled oscillator is actually giving the sine and cosine components of both the directions. Now the IQ modulator, it is at the frequency, but this frequency is synthesized in the digital domain basically, and it is provided to DAC. So it is already IF converted, but it has only structures which are required for the homodyne structure, because we do not need additional LO1 which was required in the original heterodyne structure. Similarly in ADC the signal is coming here, and we have received our in phase and out of phase by multiplying it with respective I and Q components, and after that doing the filtering, low pass filtering, to achieve our exact I baseband data and Q baseband data. So what is the main component here? The main component in this architecture is numerically controlled oscillator. Initially we were using the basically analog oscillators. Now this is something which comprise of a digital accumulator which generates the address into a lookup table which contains the stored value of a single cycle of the sinusoidal waveform. Now we can step through this table by giving that particular address, and accordingly at a adjustable rate we can have different frequencies and we can have different phases also. So if we want to say it properly, let us have an example of the 4-bit LUTs which have 16 levels. So let us say this is example of single sinusoidal case with respect to t. This is our sinusoid. So it is 16 level, so 8 level upper and 8 level lower. Right. So we have these values. So now what happens, these values, they will be stored in a particular address there, right. So these are these values which we want to read. So if we see, we have 1, 2, 3, 4, 5, 6, 7, 8, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8. These are the different levels here. Now each of these values are given in a particular address book. For example, if you want to read 1, the address will be, our positive value is 1, so it will be 3 digit value only, because we have 8 levels there. So, it will be 001, 010, 011, 100, 101. And of course, we have 000. So, these are the 8 levels which are giving these amplitude values, and similarly in the negative side we will put 1 to signify the negative value, and we can have our all these values. So, we just put 1 in front of each of them, and we can have positive value, we can have negative value. Now, let us see. So, we have seen that the upper positive levels are shown by these values, and the lower values -1, -2 are achieved by putting 1 in front of this numerical value. They are representing the negative amplitudes. So, suppose we want to read these values, these amplitudes there. So, we will read first this value. This address is storing this amplitude, then this address is storing this address, then this one is storing the next one, and as we keep going to these addresses, this is showing this direction. Now, we want to read this this sequence, then we will start going in opposite direction. So, we will start decreasing it by 1 value. Again, when you want to go that way, it is still decreasing. So, negative values will be right there, and once it goes to this direction, then it will start becoming less negative. So, in this way, these are the locations where we have stored this particular amplitude value. Okay. So, suppose we want to start from 0 phase. So, we will start our accumulator will start with 000, and then it will keep increasing 1 bit to that, and it can read the other values in this direction. Suppose we want to have a 90-degree shift, then we will have this shift will start from this point, and it will start reading these values, and when it will start reading these values, it is actually following this path. So, for 0-degree phase, it is red, black, black, red combination. 90-degree, phase difference, it will be starting from black. So, it will become black, black, and then it will be red, red. So, the black is the direction when your addresses are decreasing in nature, and when your addresses are becoming positive in nature, then they are represented by black. So, similarly, at 180-degree you can have your black, red, red, and then black. So, it will keep repeating like this. So, you can see that it is actually a rotation of the addresses which we are achieving here. So, for an example of 3-bit system, 8 address location will be there, and this is the diagram which is showing that how we can read it. The delta n is actually the sample, the difference between two samples there. K naught n is representing your address location, and as you can see, this address location is updated by del n. So, K naught n minus 1 was the previous address, and we add to it and we achieve the next location in the K direction. Now, if you want to have a phase shift, the phi n is represented here. This phase shift you can achieve by multiplying delta n's by the number of location you want to miss, and from that shift you can again take up the value of Kn and shift everything. So, this is the block diagram how it is applied. Basically, you have a sampling clock here which is going into your numerically controlled oscillator, and frequency control is applied by del n. This K naught n is implemented by a delay element which keep updating the address value, and if you have to jump the address value according to some phase control, that ON is added here, so that it can directly jump to that address from where you will start reading it. Now you have seen this with this example how you can see the phase shift there. Now suppose you want to have the frequency, you want to increase the frequency, how would you do this? So as you can see in this example that you had your 16 levels, so you have your 16 addresses. So if your sampling rate is, let us say 64 megahertz, Fs is equal to 64 megahertz. So it is sampling all these instances one by one, and it is doing 16 times to actually complete one sinusoidal. So what will be the frequency of the oscillator? What will be the frequency of this sinusoid? It will be actually 64 divided by 16. So 4 megahertz will be the frequency of the sinusoid if the frequency of the sampler is 64 megahertz. So in this way we can also control the frequency of our sinusoid. So if you want to increase the frequency, what we have to do? We have to actually increase the either sampling frequency itself, Fs, or we have to decrease our number of levels. Similarly, if you want to increase, if you want to decrease your NCO frequency, sinusoidal frequency, then you can increase the level and you will have fast output frequency from this system. So the good thing is that in this system you are doing everything digitally. So everything is much precise. You have saved these addresses with exact amplitude at this particular addresses, and by exact shift you can achieve proper phase and frequency. So they are very precise as compared to their analog counterpart. Now where can we use it? They are very useful because everything is happening in digital domain. When you have to do the filtering, you can do in digital domain. It is post processing, it is much easier than the analog filters. Analog filters also have the tendency to have some errors. They are not perfect. In digital domain you can define and you can also reconfigure these properties. So basically you are retaining the value and advantages of the heterodyne structure, but you have a small structure like homodyne structure. So how we can use it for the multiband processing? There is one example here. So in current scenario, in modern communication systems, we are mostly dealing with multiple channels, means you might be using 3G also, you might be having 4G option in your cell also, and whenever you are not catching 3G or 4G, even you will be catching 2G. So your handset should have the option for receiving all these frequencies. So this kind of architectures, this kind of front end are multi-channel, multi-band front ends. For example, if this is the frequency, this is FRF1 for one channel, FRF2 for the second channel, FRF3 for the third channel. So it is possible that you will have 3 frequencies coming, or most of the cases you will have only one of those frequencies, but your front end should be able to support any of those. So when this signal is there and these two are not, it is able to receive it, and when it is coming and these two are not there, it is still should be able to receive them. So this is that kind of structure. So in this you can see we have band select filter, so it is multi-band kind of filter. It will allow all these 3 frequencies to come whenever they are available there. Then low noise amplifier is there, so that we can have the good sensitivity when it reaches the ADC. After that we have multi-channel IF filter. After doing the first IF conversion there, again we have amplification because we have some losses in this filter. Now after that the same signal, till now we are using same IF frequency, right. So this fixed frequency we have done the A to D conversion. So in digital domain all these signals are there. So they were RF1, RF2, RF3 before, now they have become FIF1, FIF2 and FIF3 in the system. So they are in IF domain now. they are near the baseband, but they are still there. So how can we receive them? We will be dealing them like they are multi-carrier single system, and after that by demodulating them by using different NCOs, we will be getting your particular band. So NCO 1, 2 and 3 will be used to select this. So NCO 1, NCO 2 and NCO 3 will be down converting them in the digital domain. We do not need the hardware for that, they will be done, and the two components with respect to that NCO will be removed. So for this one, it will be here with NCO 1 and other two will be here, and then you will be a low pass filter which will not allow this to come, and you will get this signal. The second one with the NCO 2, how will it look? This is the baseband representation, when they say it is very much near the zero frequency. Okay, so in this case when you do the down conversion with this frequency, then your middle signal is here and the next signal is here, and the previous signal is here, and then again you select only this signal and these two signals will not be there. Same with the NCO 3, in the third case other two signal will be away from here, so you will be able to get third signal. So this can be repeated for n frequencies as shown in this figure. Things are happening in digital domain, so we are saving lots of cost in terms of hardware circuitry. So that till now we have covered the heterodyne architecture, homodyne, and then we have seen the digital IF. Digital IF we can also do the dual down conversion because in digital domain, and it will not have extra cost there, maybe processing cost, but that is more accurate as compared to their analog counterparts. Now let us go back to our original SDR concept, which was the concept of pure digital RF front ends, when we wanted to have the DSP and we wanted to send this DSP to a digital to analog converter and receive directly at the analog to digital converter and do the processing. We do not want any other analog components here. So no up conversion, down conversion is required, and we will be saving the hardware which are mixers, LO, extra filters at each stage. So what was the limitation here? Limitation was D2A and A to D speed. So in the next lecture we will be covering these two components, that is the speed limitation of D2 and A to D structures.